Hello, welcome to this afternoon's session of the TI Codes Club. This is session number 2 in a series. Now, my name is Brian Lannon. I'm your host for this session. That's me on the right there. But our main presenter this evening, can I please introduce Peter Fox from Texas Instruments Australia. Good afternoon, Peter.
Good afternoon, Brian, and good afternoon to all of those people that have joined us today.
Yes, we do have a few online. Very important topic that we're dealing with this afternoon, of course, the engineering design process. So I'm just going to hand straight over to Peter.
Thank you, Brian. So what we're looking at today is engineering solutions. And that doesn't mean we need to get a university degree to do this. It simply means we're looking at the physical, electrical, and digital content and how all of that fits together. So we're not going to be doing a lot of coding. You might see a little bit of code sitting in there. But we are going to be talking about how you find solutions and how you integrate the physical world into the electrical or digital world and combinations thereof. The way we're going to do this is through the context of a simple problem to solve. So the problem that we're going to solve is to monitor the fluid level in some sort of a tank. Now, it might be a range of different applications. There's all sorts of situations where we need to model the fluid level. We can think of the options as being binary, which essentially means off or on. A 0 state or a 1 state is what we sometimes refer to as binary. So in the case of, say, for example, a car, you'll have a windscreen water washer bottle underneath the bonnet somewhere, and it contains a liquid, usually a bit of detergent thrown in there for good measure. And most people wouldn't have a clue whether it's half full, quarter full, full to the brim or not. But what we do know is if it starts to run out, there's usually like some sort of a warning light will pop up when it's empty. So it's binary. It's either empty or full. No Schrodinger cat thing happening here, just empty or full. So a little warning light pops up on the screen. But that's not always the case. Not all fluid tank monitoring gives us just an empty or full indication. For example, we can have what's called a continuous monitoring. Now, in the case of, say, for example, the fuel gauge, it would be pretty disastrous if all it did was tell you it's empty. Imagine you're driving along the highway and then all of a sudden it goes beep, which means you just ran out of fuel. So obviously a fuel gauge, we need some sort of a monitor to tell us whether it's half full, quarter full, or indeed about to be empty. And I'm sure there's been a few people ignore that gauge from time to time and possibly run out of fuel somewhere. I've actually, believe it or not, run out as I've pulled into the service station. It literally ran out and I had to push the last 2 or 3 meters because it went up the hill to go into the servo. Yeah, I just shared that. That's pretty silly, wasn't it?
I don't think you'd be on your own there, Peter.
No, that's it.
So just on the fuel gauge, though, I think an interesting one there. Most cars actually have an example of both of those monitors that you're talking about, both binary and continuous.
They do.
When the red light comes on.
Beep sound when you get to like 100 kilometers, that one?
Yeah. Oh, that and the red light that says, you're just about out. Yeah. So it is an example of both. Yeah.
Yeah, that's right. Yeah, I'd forgotten about that. And so, well, I'll call it some of the older cars. The little fuel gauge lights up, doesn't it? And like the little E starts to flash at you or something. But you're right, it does. It has both. So let's consider, for example, the first one of binary. Now, not many people have seen perhaps the binary system on the right-hand side, but believe it or not, pretty much every household has one. In fact, some houses have like 3 or 4 of them, strangely enough. It's part of the system of a toilet. And essentially, the little black bubble thing that you can see here is a float. So it sort of monitors the water level. So if it starts to drop, then the gauge opens up and it allows the water to come flooding back in so we can flush the toilet. So it's essentially on or off. You have no idea when you go to the bathroom whether the tank's half full or completely full. You just kind of hope that it's full. But there's no gauge to tell us. So it's either running or it's not running, and that's it. So we'd call that a binary sort of an example. It's also what we call normally open. Now, Brian and I were discussing this before, and open we refer to in terms of an electric circuit. So open means a closed, or an open switch rather, is generally how we refer to that. So in this case, it's kind of ambiguous because the valve is closed to water when this thing is not activated, and it
Yes,
opens when it is. So it's
yeah.
kind of an awkward one, isn't it?
Well, I think very important to articulate the difference there. It's actually the electric circuit that's open or the switch that is open, and it's only when we close the electrical switch that it completes the circuit, which in this case will then open a water valve. So normally
Yes.
open doesn't mean that water is flowing through your toilet.
Correct. And it
All
is
the
kind
time.
of
Yeah.
weird that we refer to electric circuits that way, isn't it? That we say that the circuit is closed when the current is flowing, but a tap is closed means that there's no water flowing. So maybe we need to appeal to the powers that be that we've got that back to front. Um, but
Oh,
nevertheless,
yeah,
yep,
I like it the way it is because I think of the circuit diagram, and it
yeah,
is quite literally open, like the diagram for a switch. The lever
yes.
is open. You cannot draw a continuous path. I definitely prefer the terminology the way it is.
Uh, maybe we should have a vote. No, we won't do that now. All right. I don't think we're going to change it anyway, Brian. So we've got normally open and normally closed, and you'll find most mechanical switches will also have the same sort of thing on them. But this is one of the most common sort of water monitoring systems that is in any household. As I said, at least one you would hope in every household. Um, Now, this one is from a water washer bottle, my original example. The component is the actual component from a BMW, and if you look closely at the screen, it actually tells you BMW on the part. So there's this small float, this white plastic part is what we call a float, and then it literally, as its name says, it floats when there's fluid in the washer bottle. And you can see it's got two little electrodes. They're not actually in the water. This gets sealed in the actual tank. And then if the water runs out, that white bit drops and it levers into a switch back on the outside here that closes the circuit and, let's say, puts a little light up on your dashboard to say that the water has run out and you need to replenish it. Unlike our fuel gauge, which would be continuous, this one is binary. It's either off or it's on. It's a 1 or it's a naught. All right, let's see what that looks like in terms of a switch. So inside that mechanism, this is more of a readily accessible sort of switch that you might put on a circuit board. This is kind of like the black bit that's hidden away in that sensor that we saw before. That's one type of switch, and that's another one. This is probably the one that we're more familiar with, the one on the right. It's the one that comes in the TI Innovator System STEM kit, and it's what we'd call a slide switch. And this one is a push, the one on the left is a push and release switch. You'll also notice that there's 3 pins on the bottom of them. Now, the middle pin on each of them generally is the common. So let's say that in the switch on the right-hand side, in its current position, there is a closed circuit. That is, the middle pin is now connected electrically to the far right pin. If we put the switch the other way, then the leftmost pin and the center pin would be connected. You
So
need
Peter,
to keep this in mind if you're wiring up a circuit, because if you wire the circuit to the left pin and the right pin, there are no states at which they will be connected.
can I just ask
Yep.
there, is it necessary for that all 3 pins are connected to something?
No, that's a good question. In some circuits, it would if you want to toggle between one object and another. So switch one thing off and maybe something else on. So it might be switch the fan on to cool something or switch a heater on to warm it back up. So you could have it literally so you would toggle one way or the other, that something is always going. But no, you're right. It's not necessary because closing the circuit between, let's say, the left pin and that middle pin, if you don't want it to do anything, then literally don't connect it to anything.
Very good. And I think
Although,
that's a good
having said
example of
that,
our open and closed.
yeah, having
Yeah.
said that, of course, you would probably want to put some sort of a shield over this other pin if this is connected to the active. In other words, if this is 5 volts, then when you slide that switch the other way, then the 5 volts is live there. So you'd probably want to have that pin covered up if it was being physically wired as opposed to on a breadboard where it could just be going to a separate point. Now that's the other interesting part here. The pins on this are not designed to go into a breadboard, whereas the ones on the left, they are designed to go into a breadboard. You can tell by the really narrow pins here, they will actually slot nicely into the breadboard that comes with the TI Innovator kit, the STEM kit. So in the circuit that we're talking about before, say for example, monitoring the fluid in a bottle, you would probably want to use the one on the left and ditch the one on the right. The reason being, of course, and think of this in a practical sense, if the water washer bottle is empty, you top it up, you kind of expect the red warning light to switch off. Now, in the case of the switch on the right, you would also have to find the switch and reset it. So it's not really the type of switch we want for this case. We want one that's going to reset, so this metal lever here is spring loaded and will bounce back into position in the case that the circuit or the condition has gone away. That is, our water is now being topped up. Now I did make a little physical model. I've got a webcam here, but the webcam is more for my next model that comes up later. This is just one using some Lego parts. It's very primitive. I'm sure students will make something a lot more sophisticated than this, but you can see you can gather resources that you may have sitting around the house. It's probably a little bit weird that I've got all this Lego sitting around the house, but that's the way I am. And there's a switch over here, so I've used the actual Lego switch because there's wires under there that I can access. And it's just a switch. It's just going to connect 2 wires together. That's all it does. And this little orange bit here is spring loaded. So as that goes up, the fulcrum is down on the left here. So this arm will rotate and release the switch. This plastic hollow ball will float. So it literally just, if this was sitting in water, not the switch obviously, this has got to be sitting in the water this end, very important to know that. And it literally, as the name describes, floats to the surface. So it physically pushes the arm up and releases the switch. Or when the water level drops, the ball sits on the surface of the water and then pushes that pin in when it gets empty. You probably remembered, Brian, like I do, the old days of carburetors in car engines.
Absolutely. Yeah, I've messed with a few of these things, Peter, over the years. Certainly the toilet system, where I've often had to replace valves on that. And of course, the old thing with a car carby was that if you have run out of fuel, often to get the thing going again, you just throw a little bit of fuel in the carby once you fill the tank up as well.
That's it, because the float was empty. The little
Yeah.
it's a little floating ball, if you like, or tank that sits inside the carburetor, and it's supposed to hold fluid in there. And sometimes the little needle in there, which is the valve that allowed the fuel to come out, would get stuck. So that was another thing you had to replace in those. But nowadays we have fuel injection. But those things still existed, a very common sort of setup. So let's have a look at a really simple circuit. And we're monitoring, let's say, fluid in a tank. So we've got some sort of a switch. So we've looked at the mechanical part where there's a lever and a fulcrum and all of those sorts of things. Now we're having a look at the electronic side of it. Some sort of an LED. Back in the days of carburetors, they were incandescent globes. They're a lot more energy efficient now, a little LED, a lot longer in lifespan too, I might add. And a resistor. And we'll see why that sits in there in a minute. And this is what Brian was talking about, being able to physically put your finger on the circuit and trace all the way around. We can't trace because there's a gap. So that switch is currently showing that we are open. That means we have no electricity coming through the circuit. When that switch closes, those contacts are made and the electricity will flow through the circuit. So in the case of TI Innovator Hub, your supply voltage is about 5 volts. You might use different circuitry other than the Innovator Hub. It depends on what part of it you're doing. But you might as well, because it's got a nice little 5-volt supply in there that we can utilize. Diodes tend to run about 20 milliamps. That's a very, very small amount of current, and it's important that you know some of these things once you start to build the circuits. And we need to know this handy little law here called Ohm's law. It's very simple. Voltage equals current and resistance. So I want to work out what resistance I need. I've got 5 volts, that's the V. I've got a current of 20 milliamps, so we need to know our scientific notation. That'd be 20 by 10 to the minus 3. We transpose it to make R the subject, and we can work out resistance. So let's do an example. Now, I've drawn the circuit a little bit different just to make it easier to follow. So we've got 5 volts over here, 0 volts at the ground, as we call it. And here's our color chart. So the red diode that I was using, about 2 volts, but you could change it to a different colored LED, 20 milliamps. And Kirchhoff's law says we add the voltages up. So I've got 2 volts here, which means I must have 3 at the actual resistor. And it's a series circuit, so it's still 20 milliamps. As I said before, we rearrange the formula to make R the subject. 3 divided by 0.02, I've done the arithmetic, it's 150. And then we can wire up the circuit. And when it comes to physically wiring it up, you might not get 150 ohms, so I might use a 220. That just means our diode won't be quite as bright, but no big deal, it's still going to be bright enough to see. And here's the color, here's the color coding for our resistor. There you go, there it is. So they have these colored bands in there. And you can download these from the internet, look it up. That's basically what I've done, is just looked up these color coding bands. 220, red equals 2, so 220 times 10 to the 0. 5% is a gold band. So I've got my resistor plugged in there. And my diode will come on as long as this circuit is complete, which means I need to put the other end. So I've got one end going to the positive part of the breadboard, and then the other end will go to the negative part of the TI Innovator Hub's breadboard. You'll see it's got that little earth symbol down the bottom. The actual breadboard that comes with it, the positive rail or supply rail, that's all those little dots across the top, and then the negative one just below it. And you'll see you've got another branch down the bottom, which is exactly the same. And for all the pins in the middle, they're connected that way. You can see they've got numbers. So all the pins on 30, A, B, C, D, E are joined. And F, G, H, and I and J are joined to one another, but E and F are not joined unless we do it. It's going a bit fast here. It's on automatic pilot. So what do we do next? Well, we can run the positive lead into the positive supply rail, into a resistor, into our diode. The longest end, the larger end of the diode is the positive end. Positive numbers are bigger than negative. And the negative terminal just comes back to the TI Innovator Hub. So that's your basic circuit on how to wire it up. All right, where to next? Analog or continuous ultrasonic ranger is another sense that we can use. So we've looked at the binary, a switch just coming on or off. Now we'll have a look at this idea of a continuous or analog sensor. Ultrasonic range is one, and believe it or not, some cars, Brian, now have ultrasonic sensors in their tanks.
Okay.
So they're using sound to detect how much fluid is in the tank. That's pretty cool.
That is very cool, and I think it's very cool that that our students engaging in this contest get to actually play with some of these building block technologies. That's my view of it. You know, how would you use an ultrasonic sensor to gauge the height of a liquid? Can you design something
here you go,
like that?
Brian.
Yeah.
Here's a question for you. Whereabouts, other than some fancy cars that have them in the tanks, whereabouts would you also see an ultrasonic sensor on a car?
I'm not that my car has this, Peter, but I'm thinking these reverse sensors and
Correct.
lane. Yeah. Yep.
Yep. So if you have a look on the bumper bar, some cars have them on the front as well. So I used to refer to them as reverse sensors. My son has a car that has it on the front and the back, and some cars have them on the side as well. It's like they're positioned all around the vehicle, so they know when something is near them in either or any direction. But yes, you'll see a lot of them in the rear bumper bar, as you rightly point out. They were referred to as reverse sensors originally, but now they're becoming all over the all over the car.
Yeah, I think especially on the side, really, really relatively simple technology, and so helpful.
Well, that's right. In fact, the very simple one is now I drove, I think it was a Commodore one day, and I've seen lots of other cars like this. My car doesn't have it, where, as you say, they have them on the side of the car, and you'll see a little light pop up in the rear view mirror, indicating that there's a car to your right or a car to the left. And it's just one of those ultrasonic sensors that says, okay, my field of view just got blocked. That means there must be something off to your right. So it's a lovely little example of a warning light that pops on when the sensor's being changed.
Yes. Yep. No, very good.
Look like that. Really simple. So it's ultrasonic. You won't hear. That's the whole idea of why it's called ultrasonic. Sonic meaning it's got sound. Ultra basically meaning it's a frequency that we don't hear. So just because when you turn it on, you can't hear it, that doesn't mean it's not working. And you'll see one has a little T above it. That's a transmitter. And the other one, R, is the receiver. So the sound is transmitted or pumped out from here, and then it's received in the other one. So if you were silly enough to put your finger over one of those, then it will never receive the return signal. Now, not that I'd necessarily encourage this, but interesting question. If you have two identical cars and you're reversing towards one another, would you actually trick them in some way? So the sound that pops out of here, let's suppose you and I, Brian, are reversing towards each other and we had exactly the same car. Mine is emitting this sound and it's coming out of my bumper bar and it hits the receiver on your bumper bar. Does your car know that that's not the signal that it sent? Are they actually encoded in some way?
Yeah, I'm just wondering, are they on different frequencies or are they on a set frequency?
Yes. And you'd think perhaps a single manufacturer may just be really lazy and leave them all on the same frequency, in which case it could be an interesting test to see what happens. And just be very careful if you do that, just in case, because maybe it does mess up the signal. Now, we do have another webinar coming up, which looks at receiving signals and how to actually program them. And we'll probably be covering this particular one because it's very easy to set up and it's very useful. Another spot you'll see them if you're using the hand sanitizers at the supermarket and you put your hand in there and the spray is supposed to come down. Well, that's a classic example of a sensor that's just detecting that some movement happened. The distance, the standard distance to its actually it's time, the time it took for that sound wave to come out of there and reflect back into there suddenly changed. So it then says, okay, well, I'll squirt some sanitizer onto your hands. Assuming, of course, the bottle is full. Because if the bottle's not full, it's not going to squirt anything. All right, now another one. This one is also an analog device. And this one comes in the Innovator kit, the little STEM kit with all the little components in it. So I decided I would make one of those. Or make a circuit or a physical model with one of those on so you can see how that works. So this one is essentially just a variable resistor. So how does that work? Well, it actually has 3 pins on it. And the center pin, in this case, is where we sense the change in the resistance. So we can put supply in on one side and earth on the other. And then this little arrow is signifying like you can just rotate that thing and it's pointing to some sort of resistance. So how does that work? Here's a little model I've made up and I'll just run through it. Then we'll test to see if my webcam will pick it up and my software will actually detect the change. So you can see what we mean by an analog sort of a sensor. So the wiring we can see on the left-hand side of screen, positive wire, that's going to one side of that variable resistor. The black wire is going to the other side of the variable resistor. And then on breadboard input number 5, and you need to check the website, I'll show you that in a moment, to see what pins can go where, what ports you can set up as digital and analog, sensing, in, out, etc. So I've got port 5 on the breadboard set to just monitor the voltage level. So in my program, I said, well, I'm just going to supply a constant voltage output. So I said, I'll just use digital and just switch on. It's a really simple thing, just digital output, switch on. So it's just supplying a low current 5 volts through this variable resistor. Again, I've used my Lego. It says something about me, I guess. And I just used a hot glue gun just to attach a Lego piece to the top of that variable resistor. And it's attached to this cog. Now that again comes back to our physical design, our engineering. You need to think about how much the lever, which is just off the top of the screen at the moment, how much does that need to turn in order to move this? So I needed to gear mine up. So in other words, one revolution of this, which is about 50 little teeth on that one, goes to about 25 or 20 teeth on that. Let's do some easy numbers. Let's suppose there's 25 teeth on that one and 50 on the other one. That means a half turn of the top one will give me a full rotation of the bottom one. Now your variable resistors, generally about 270 degrees, not temperature, rotation, because it's a sliding disc that's sitting in there. So it can only slide around about 270 degrees from full on to full off, or full off to full on. So you need to consider those things when you're designing. So the 3 pins are attached on the breadboard. That's the little breadboard that comes with the kit. You can see the numbers 1, 2, 3, 4 all the way through to 30, A, B, C, D, E, etc. So anything that's connected in line 1, A, B, C, D or E, is automatically electrically connected to each other, but not to line 2 or line 3. Now I didn't need to use the supply rail on here because I've only got one component on here. So I just went straight from the positive on the breadboard into one side of the variable resistor and the negative straight into the negative. I could have gone through the supply rail. It just would have meant an extra wire, which would have made this a little bit more crowded. So now let's see if I can bring up my webcam. Are you able to see that, Brian? It's a little bit blurry, but...
Yes, that's looking good. I've just typed in
right.
that I'm just loving the mix of maths and science and engineering here. And now you go and wow us with even more technology.
That's it. Well, this
all
is
there.
Lego. It's kind of simplistic, but it works. And now the other thing is you don't need Lego to do this. You can use bits and pieces from around the house. This could have been done just as easily with icy pole sticks and ping pong balls to work as a float. Just remember, if you're using liquids, keep them away from the electric circuit board. So you'll need something physically in the way to stop them getting in. You don't want water in the circuit. It doesn't work well at all. So this little lever on the top, if I rotate that, it's actually glued to that variable resistor and it's rotating. If you have a look down the bottom here, you'll see as I rotate it, that's rotating the resistor. Now at the moment, the TI Innovator Hub is reading that change. It's reading it as a different voltage because it's having to go through more or less resistance as that rotates. So now let me swap across to, and this is the first time you've seen some code. Now in our later sessions, we're actually covering how to code, and you can choose whether you want basic, this one's basic, or Python. Some students might like to use Python. So we haven't covered that in this session, but that's on purpose because that's coming up. And what we're looking at here is what's going to be covered in the last 2 sessions. So this one, we're connecting digital out to breadboard port 1. So that's putting output, putting a voltage out of breadboard 1. I've also connected an input, analog in, and that was connected to breadboard port 5. And I said, let's just run a sample of 100 points or 200 points. So I've said, how many would you like? And then it's going to store the data. So let's go into here. You can see in the background there, I've already run one before. Let's bring up the calculator. So the program's on page 1.1. On page 1.2, I can just go ahead and press enter. It says, how many samples would you like? I'm going to do 120. Now, it's not doing one every second. It's just however fast it's going to collect them. So then I'll click on OK, and you'll see I'm just rotating the arm now and see that the numbers are changing. So that's fully to one side and then going back again. And that's all its samples. So that's what that looks like over here at 120 samples. So you can see I rotated in one direction, stopped, and then rotated back the other direction. So this might be full tank of fuel running down. It'd be nice if you could just do a lever nowadays, $2 something a litre, and then empty. And now I'm filling back up again. Now these numbers are meaningless at the moment. They're just measuring a degree of voltage. It's basically an analog to digital converter. So it's just assigning a number. So you would need to calibrate that. So if it was full at this voltage, then that would be some condition. And then you might say, if voltage less than this or number less than this, then switch a light on or something like that. All right, so that leaves us to what's coming up next, Brian. So on Tuesday, I'm probably choosing your pinching your thunder here, am I? That on Tuesday, the 22nd of March, you get to choose your language. That would be BASIC or Python. And then on Tuesday, the 29th, we have the inputs, a bit like the ultrasonic sensor or that verbal resistor, and then selecting your hardware outputs. That is like whether you want lights, pumps, motors, those sorts of things, and how you connect them. So we're doing programming examples on the 22nd, and the inputs on the 29th, and outputs on the 5th. And for those football enthusiasts, we've also got one on the 30th of March. Have we got any time for me to plug that, Brian?
Yes, look, I know I'll be very keen to attend that one, Peter. I reckon you've certainly caught a big fish to help in the hosting of it.
I like that. Yes, we have a guest appearance from a former AFL legend. A bit of a clue in there. And then when you go to register, we've even set the page up. Doesn't that look familiar? Doesn't that look exciting there? Look at that. Remember those days? They're back.
Very exciting, Peter. In fact,
so we'll be talking all things statistics and, believe it or not, STEM as well.
Can I just mention I'm very much looking forward to being at that very venue tomorrow evening.
Very nice. So 30th of March, good one to watch out for. Well, that's about it from this end, Brian. I think we're just about out of time, aren't we?
We are. I'm just going to swap back to my PowerPoint just to close us out here. But when I do that, it's the invitation to our participants to post any questions to Peter there, and just type into the chat, hit the speech bubble down at the bottom right of your screen. And there've been a couple of questions there, but I think we addressed those as we went on. So couple of minutes now just for your opportunity for that, and either way we hope that we can see you again same time next week. If you wish to review the recordings, check back through the text that I've posted in the chat, because I have got links there to the various recordings, either on our webpage or on the Texas Instruments Australia YouTube channel. Okie doke. So once again, thank you for joining us, and hope to see you again next week. Thank you again to Peter. I shall close out our session now.